During the last lecture, we have seen motion along a straight line, and now we will extend our discussion to 3 dimensions. We will use vectors to represent the position and velocity of a particle in 2 or 3 dimensions. We will also investigate the vector acceleration of a particle. We have learned that acceleration is a vector and it has vector components, okay? Components of acceleration parallel to and perpendicular to a particle's path. Today we will see all these things. In addition to that, we will deal with problems that involve the curved path followed by a projectile. Projectile in Turkish mermi. Okay, and next lecture on Thursday, we will continue with motion in a circular path with either constant speed or varying speed, very important topic in physics. And then we will deal with the velocities of a moving body as seen from 2 different frames of reference. This is also another important topic of this chapter. And today I would like to finish these 3 parts, and circular motion and also different frames of reference will be discussed on Thursday. So now I have few questions. Here you see racing cars, and they have more or less a circular or curved path here. So how do you describe the motion of the car along the curved path? So after this chapter, you will able to explain the behavior of these cars. In addition to that, for defense applications, this is very common application in defense industry. So what do you see here? This is a projectile and this is Fırtına howitzer. Okay, so what do you see here? This projectile has certain trajectory in 2 dimensions. Okay, so now we have a question. What determines where a projectile lands? So what is the final position of this projectile? And what is the maximum height of this projectile? What is the maximum displacement along the x-axis of this projectile? So we can able to answer all these questions after this chapter. And here another question. Here we have 2 balls. One is yellow ball here on the right side, and on the left side we have a red ball. So the red ball is simply dropped. It has free fall motion, okay? And yellow ball is thrown horizontally. Then it has this type of motion. So now the question, which hits the ground first? Okay, so we have to answer all these questions, and the information within this chapter will help us to discuss all these things. Okay, now let me introduce a position vector. This is new term for you. So what is the position vector? The position vector is showing us the distance from the origin to the particle, and it is shown by small r. Of course, it is a vector. So this is the position P, and this vector from origin to this point shows us position vector. And what do you see here in 3 dimensions? Here we have x-axis, okay? Here we have y-axis, and here we have z-axis. And this position vector has 3 components, right? And I can write this position vector in terms of its components. This is the x times I unit vector along the x-axis plus y times j unit vector along the positive y direction, and then plus z times k unit vector along the positive z direction. Now let's try to define average velocity by using this position vector. During the last lectures, we have learned that average velocity can be written by delta x over delta t, displacement, okay, right? But here what we have, instead of delta x, we have delta r. it contains 3 dimensions. This one. If you are talking about motion along a straight line, as we have done during the last lecture, for example, this will be 0, this will be 0, and r will be equal to x times r. Okay, this is motion along a straight line. But here we have 3 dimensions. So in order to calculate the average velocity in 3 dimensions, we use change in the particle's position vector over delta t, and it is r2 minus r1, final position minus initial position, and t2 minus t1. So what about instantaneous velocity? Instantaneous velocity defined by when the delta t goes to 0 for a very short moment, let's say, and it is given by delta r over delta t, or it can be written by time derivative of the position vector like this. Do you have any question? Nothing is new here for you because you have already learned all these things, but we only write this average velocity and instantaneous velocity in 3 dimensions. Okay, now let me show you the average velocity and instantaneous velocity on a graph. Here we have x-axis, here we have y-axis, here we have z-axis. This is the particle's path. Let me draw with another color and then you will better see it. Here we have a particle and then it is moving along this path. This is the particle's path, and I am choosing 2 positions here on the path. This is the position 1, and this is the position vector from origin to the position 1 when the time is at t1. This is r1, and here I have chosen another position, position 2, and this is the position vector from the origin to the position 2. So what do you see here? This is delta r, displacement vector delta r points from P1 to P2. So here from position 1 to position 2, we have displacement vector. So have to find this displacement vector. What was delta r? Let me write delta r here. Delta r is r2 minus r1. So what do you see here? Vector subtraction. r1 is this one and r2 is this one. How to subtract vectors? We have learned during the first chapter. So you have to put them tail to tail, right? This is the first vector, r1, and we have the second vector, r2. In order to get this subtraction, r2 minus r1, you have to put them tail to tail. And then the vector from head of this vector to the head of this vector will give us the resulting vector, right? Delta r. So here we have delta r. This is the displacement vector. And we are looking for the average velocity. Here we have average velocity is given by delta r over delta t, and delta r is this one, and delta r over delta t is giving us the average velocity. So the average velocity is along this direction here, this green color, okay? But what about instantaneous velocity? So don't forget this, average velocity is along the direction of delta r, but instantaneous velocity is always tangent to the path at each point. Now let me draw. This is the particle, and then this is the path of the particle. The particle is moving like this. And now I would like to find the instantaneous velocity vector when the position is P1 and velocity is tangent to this path, okay? Here, I would like to find the velocity vector when the position is P2 and velocity 2 is tangent to the path, okay? Do you have any question here? Now let me continue. So instantaneous velocity is the instantaneous rate of change of position vector with respect to time. And it also has components. And we can write the components like this. X component of instantaneous velocity is given by dx over dt. Look at the definition. Can you see the definition here? Instantaneous velocity vector of a particle is given by dr over dt, time derivative of the position vector. So what we have here, r. What was r? Position vector. And position vector has three components, right? X, Y, Z components. So if I take time derivative of these components, then I can get the components of instantaneous velocity. This is the x component of the instantaneous velocity, which is given by dx over dt, and y component of the instantaneous velocity, dy over dt, and vz is dz over dt. And if you would like to write instantaneous velocity with this all components, which is given by time derivative of the position vector and time derivative of its x component times I unit vector plus dy over dt times j unit vector plus dz over dt k unit vector. And what about the magnitude of this vector? Magnitude of this vector is given by this expression, vx squared plus vy squared plus vz squared, square root of this term. This is the magnitude of instantaneous velocity. So here we have a two-dimensional motion. This is the x-axis, this is the y-axis, and this is the particle's path. Let me show you again with red color. Here we have a particle, and in two dimensions, the particle is moving like this, okay? The particle's path in the xy plane. This is the x-axis, this is the y-axis, and this is xy plane. So I would like to get the instantaneous velocity at this position. The instantaneous velocity vector is always tangent to the path. So then the velocity is given with this direction. This is the instantaneous velocity at this position. And this velocity has two components, Vx component and also Vy component. And this is the angle alpha, okay? The angle between positive x direction and velocity vector alpha. For the position vector or for the displacement, we have used theta, and for the velocity, we will use alpha, okay? The angle from the positive x-axis to the velocity vector. Do you have any question here? For this example, for this condition, the magnitude of instantaneous velocity is given by square root of Vx squared plus Vy squared. And I would like to calculate angle, for example, here, alpha. So the tangent alpha is given by Vy over Vx, you know, from the trigonometry, right? Do you have any question here? As I told you, we use alpha for the direction of the instantaneous velocity vector to avoid confusion with the direction theta of the position vector of the particle. So here we use alpha. Okay, let me show you an example. This is the example 3.1 from the book. Let me read the question first and then go into detail. A robotic vehicle or rover is exploring the surface of Mars. The stationary Mars lander is the origin of coordinates, and the surrounding Martian surface lies in XY plane. The rover, which we represent as a point, has X and Y coordinates that vary with time. So the rover, robotic vehicle, is traveling on Mars surface, and then its X position and its Y position are changing by time. So they depend on the time. So it is given by 2 meter minus this term times t square. And the y position is also given by this term. So let me check the units. This is meter, position must be meter, right? On the right side, we have meter per square second, but here we have square of second again, and this square second cancels this one, and unit again meter. And here, look at this one, meter per second. Here we have another second, and unit of this term will be meter. And here on the right side, again, we have unit of meter. Units are very important when you are doing calculations, don't forget. So now we have questions. Let me show you a picture. This is the picture from the NASA, okay? So this is the rover, and it is traveling on Martian surface. So the question is related to this one. So now let me go back to the question. Find the rover's coordinates and distance from the lander at time is equal to 2 seconds. Part B, find the rover's displacement and average velocity vectors for the interval time 0 second to time 2 seconds. Displacement and average velocity. Find a general expression for the rover's instantaneous velocity vector. Express v at t is equal to 2 seconds in component form and in terms of magnitude and direction. So first of all, we have 2 seconds. Just take 2 seconds, put here, and put here. You can calculate the x and y coordinates, and the distance from the origin you can easily calculate. And the second question, displacement and average velocity. Displacement is given by delta r, right? So that if you find the delta x, delta y, you can calculate delta r. And here we have average velocity, which is given by delta r over delta t. You can also calculate this one. And time interval is this one, 2 minus 0. So the last one is general expression for the rover's instantaneous velocity. Go back. Instantaneous velocity is given with this expression, dr over dt, or dx over dt I plus dy over dt j, okay, with this term. So if you know the x, if you know the y, if you know the z, and if you take time derivative of this components, then you can calculate instantaneous velocity in terms of time, right? Here we have x and y. If you take time derivative of these two positions, then you can get the general expression for the rover's instantaneous velocity vector. Let me show you this graph here. So here we have x. Just consider that the time is 0 at the beginning. Time is 0. If the t here is 0, then this term, the second term, will be 0, and the x position will be 2 meters, right? X position is 2 meters. Okay, it has just x component. And when the time is 0, this component of y will be 0. This component of y will be 0, right? And then y will be 0. So when the time is 0, there is no y component. So we have just this position for the rover on the Martian surface. And now let's have a look. If I put here 1, if I put here 1, and if I put here 1 for the first second, then I will have another position which will have x component and also y component. And if I put here 2 seconds, 2 seconds, 2 seconds, then I have another vector, position vector, and I have another x component, another y component. So what do you see here? This is the rover's path, okay? Rover is started from this point, and then it goes along this path. So what is this V0, V1, V2? These are instantaneous velocity. And what you see here, this instantaneous velocity is always tangent to the path, tangent to the path. tangent to the path. Is it clear? Do you have any question related to this part? Then let me continue. What was the first question? Find the rover's coordinates and distance from the lander at 2 seconds. So x is given and y is given. Instead of t here, just use 2 seconds. And then x coordinate is 1 meter and y coordinate is 2.2 meter. And what about the rover's distance from the origin? It is given by the position vector r, and it is given by the square root of x squared plus y squared. So just put these numbers here instead of x and y, then you can calculate the distance from the origin for the rover. It is 2.4 meter. So when the time is 2 seconds here, right? The distance from the origin. Okay, now the second question. Find the rover's displacement and average x velocity vectors. So what was displacement? This was the initial position of the rover. This is the final position of the rover. So we need displacement. Okay, so in order to find the displacement, first we express the position vector as a function of time. So here we have position vector, which is given by x times unit vector along the x plus y times unit vector along the y. So just put here x, this one, take this one, put it there. And here we have y, take this y, put it there. So when the time is 0, just put 0 here instead of time, r0 here, the distance of this initial point to the origin, okay? Or the vector from origin to the initial point, r0, is given with this expression, 2 meter I plus 0 meter j. So this y component is 0 because it is only has component along the x-axis. So now when the time is 2 seconds, just write 2 seconds here instead of t, 2 seconds here instead of t, 2 seconds instead of t here. And then we have already calculated. Then we have 1 meter I, 2.2 meter j, okay? Then we have calculated R0, we have calculated R2. What is R0? Initial position. What is R2? Final position from the origin, okay? And the question, what is the displacement? Displacement is delta R, R2 minus R0. Just use this ones and put it there. So finally you can find displacement. Another question is average velocity. Average velocity is given by delta R over delta T. Put this delta R here. Delta T is 2 seconds, okay? Then you can find average velocity. What do you see here? Look at the unit. In delta R, here we have meter, here we have meter, but in case of average velocity, meter per second, because here we have delta T, okay? Don't forget. And what do you see here? We have negative number for the x component of the average velocity. Why we see negative component? Because look at the average velocity. This is instantaneous velocity. This is instantaneous velocity when the time is 0. This is the instantaneous velocity when the time is 2 seconds. And what about the delta R? Let me show you the delta R. You can consider that this is delta R, okay? Displacement R2 minus R0. And we average this one will also be along the delta R. This is the direction of the V average. And what do you see here? If you take the components of this V average, this V average has two components, Y component and X component. This is Vx, this is Vy. And what do you see here? This Vx is negative because along the negative X direction, and this Vy is positive because it is along the positive Y direction. Do you have any question here? What was the final question? general expression for the rover's instantaneous velocity vector v. So in order to write the general expression for the instantaneous velocity, we have to write Vx times I plus Vy times j. So what is Vx? Vx is given by dx over dt. So you will take the time derivative of x. X is this one. Here we have x, here we have y, and I need time derivative of this x and time derivative of this y to find the instantaneous velocity. So here we have Vx, dx over dt, time derivative of x and time derivative of y. If you take the time derivative of this x and y, you can calculate Vy and Vx. And if you put them here, you can calculate instantaneous velocity as a function of time, and this is general expression for the instantaneous velocity. And for the time is 2 seconds, just put here 2 seconds instead of t. Just put here 2 seconds instead of t, and then you can calculate v2x. What is this v2x? X component of velocity when the time is 2 seconds, y component of velocity when the time is 2 seconds, and the magnitude of the velocity is given with this expression. Put these components here, then you can calculate magnitude of velocity when the time is 2 seconds. And if you would like to find the angle when the time is 2 seconds, what is the angle between positive x direction and this instantaneous velocity when the time is 2 seconds? So the angle when the time is 2 seconds is given by arctangent Vy over Vx is given with this expression. Then alpha is 128 degrees. The angle between positive x direction and the instantaneous velocity vector. This is the alpha. Do you have any question related to this example? Okay, then let me continue with the acceleration vector. You have already learned the acceleration. What is acceleration? What is acceleration vector? But if you have a curved path, then the direction of the acceleration is a bit different from the acceleration in motion along a straight line. So here, during this lecture, we will see all the things. And please try to stay on the line and listen carefully. If you don't understand this part, then you cannot catch other forthcoming transparencies. So here we have a car. This is the first position of the car, initial position of the car, and it is going along this curved path, okay? This is the second position of the car. What do you see here? This is the instantaneous velocity when the position is P1. This is the instantaneous velocity when the position is P2. So here, the velocity when the position is P1 is bigger than the velocity when the position is P2. So the magnitude of V1 is different from magnitude of V2, right? But here we have another different thing between these two positions. What is the difference between these two positions? Who can tell me?
The direction of the vector.
Yes, very important. The direction of the instantaneous velocity is also different for both positions, right? Here, the direction of the vector is like this. Here, the direction of the vector is like this. This is the magnitude of second vector. This is the magnitude of the first vector. So both magnitude and direction are different. Let's consider this is V1 and this is V2. These are vectors. And from the first chapter, we have learned that vectors have magnitude and direction. So what do you see here? Magnitude of V1 is bigger than the magnitude of V2. But in addition to that, if you draw here the coordinate axis, this is x, this is y, and this is alpha 2, and this is alpha 1. So what do you see here? These are completely different vectors, both in terms of magnitude and direction. So what was the acceleration? Acceleration is given with the time derivative of the velocity. So here, since the velocity changes, then we have acceleration here. Okay, so within this lecture, we will try to calculate acceleration and we will try to find the direction of the acceleration. Let me continue with the definition. This is the average acceleration, and this is the change in the particle's velocity, delta v, final velocity minus initial velocity, and this is delta t, time interval, right? Let's consider that v2 is equal to v1, both in terms of direction and magnitude. Then this will be 0, then the acceleration will be 0. If the velocity is constant, if the direction of the velocity does not change, then acceleration will be 0. There will be no acceleration. In order to have acceleration, we need change in the velocity. But now I'm asking a question. So this is the most important question of this lecture. Let me draw two vectors. This is the v1, let's say, and this is the v2. Let's consider that the magnitude of v1 is equal to magnitude of v2, right? So they have same magnitude. But what about the direction? The direction of v1 is completely different from the direction of the v2, right? So then these two vectors are not same, so velocity is changed. If the magnitude here is constant, but if the direction is changing, then we have acceleration here, and this acceleration is constant. Okay, I will go into detail in motion in a circle on Thursday. So now let me continue with the instantaneous acceleration vector, which is given by limit delta t goes to 0, delta v over delta t, or time derivative of velocity. Okay, again, what do you see here? This is vector, and it has both components, magnitude and direction. So if one of this magnitude or direction change by time, then you have instantaneous acceleration. Okay, don't forget this one. So now let me try to find the direction of the acceleration. Here I have a curved path, and this is the initial position of the particle. Particle is moving along this direction. This is the second position of the particle. And instantaneous velocity is tangent to the path. Instantaneous velocity is tangent to the path. So this is initial velocity, this is final velocity. Now I would like to calculate delta v. What is delta v? Remember the vectors, v2 minus v1. What is this? Vector subtraction. How to subtract vectors? In order to subtract vectors, you have to draw a vector here, and you have to put them tail to tail. This is v1, this is v2, and delta v is this one. Vector subtraction, v2 minus v1. So this is the direction of the delta v. Okay, and what about the average acceleration? So we have found the direction of the delta v. Delta v is this one, and average acceleration is given by delta v over delta t. So average acceleration is along the delta v. This is a new information for you. So here we have velocity in this direction, but the acceleration vector is along the different direction. Okay, so you must be very careful with a curved path. Do you have any question here related to the direction of acceleration for this example? So first of all, we have velocity 1, instantaneous velocity, we have velocity 2. By using the vector subtraction, you can find delta V. This is the direction of the delta V. We have found it here. And acceleration is given with this expression. So average acceleration is along the delta V, okay? Remember the motion along a straight line, which we have seen during the last lecture. This was the origin. This is positive x, this is negative x. And then, let's say this is the direction of the Vx. This is the direction of Ax. So then the particle is speeding up along the positive x direction. Or it can be like this, Vx like this and Ax like this. The particle is speeding along the negative x direction. Or we have another two conditions. I'm talking about motion along a straight line, last chapter topic. And now I will explain what is the difference in between. So let's consider this is the direction of the Vx and this is the direction of the Ax. They are opposite to each other. So then the particle is slowing down. Here again, this is the direction of the Vx and direction of the Ax. They are opposite to each other. So the particle is slowing down along the negative x direction. So this was the motion along a straight line in one dimension, right? In two dimension, like here along a curved path. So this is the direction of the velocity, but acceleration is along this direction. So it is completely different compared to the motion along a straight line. So in motion along a straight line or motion along the single axis, acceleration vector is either parallel or antiparallel to the velocity. But here we have acceleration which is not parallel or antiparallel to the velocities. The acceleration is along the delta V vector. Okay. Do you have any question here? Let me discuss another example here. Let's consider again the same curved path. And then we have two positions. This is the initial position and velocity tangent to the path V1. And this is the second position tangent to the path. What do you see here? We have magnitude of V1 is equal to magnitude of V2. Only their directions are different. Here we have bigger magnitude of V1 compared to the V2, but here we have same magnitudes for V1 and V2. What about average acceleration? So since it is given by delta V, then I have to find the direction of the delta V. So what is the direction of the delta V? Just take this V1 here and V2, tail to tail method, right? We have to do subtraction because this delta V is given by V2 minus V1, okay? So this is the direction of the delta V and also the direction of the average acceleration. So here we have constant speed. I mean, the magnitude of velocities are same, but since the direction of the velocity is changing, then we have an acceleration. Don't forget. Do you have any question? Okay, let me continue with the instantaneous acceleration. I have already discussed all these things, but I will repeat the information here again within this transparency. So we have velocity vector, this one, instantaneous velocity, V2, V1. And what about instantaneous acceleration? So instantaneous velocity vector is always tangent to the path, right? But instantaneous acceleration vector does not have to be tangent to the path. So as we have done it by using vector subtraction, we have calculated delta v, and we have shown the direction of the delta v, and then this is the instantaneous acceleration vector, okay? If the path is curved like this, or like this, acceleration points toward the concave side of the path. Do you have any question here? Okay, as I have discussed in the previous transparency by drawing, so here we have a condition for the motion along a straight line. Only if trajectory is a straight line, as we have done in the previous chapter, let's consider this is positive x direction. Here we have position 1, position 2, velocity 1, velocity 2. What do you see here? If the particle is speeding up, then we have bigger velocity here in position 2, and this is the delta v along this direction. This is the acceleration along the delta v and along this axis, okay? So then the acceleration is tangent to the trajectory. Velocity is along this axis, and acceleration is also tangent to the trajectory. And it is only valid for the straight line motion. But in case of a curved path, then the acceleration points toward the concave side of the path. Now, let me discuss the components of acceleration. Look at this one. This is acceleration vector, right? If you choose an x-axis like this and y-axis like this, I can write this vector in terms of x and y components, right? Now we will do this one. This is the x component of the instantaneous acceleration vector, which is given by time derivative of vx. This is ay, this is az. These are the components of instantaneous acceleration vector. Here we have an example, shooting an arrow, okay? Acceleration vector is this one, along the arrow, let's say, and this is the x component of the acceleration vector, and this is the y component of the acceleration vector. Here I would like to give you one nice information from our history. This is the picture of Kemankeş Toskoparan İskender from the Ottoman time. This Kemankeş has a world record, drove an arrow to the x distance of 846 meters. What is the meaning of this one? So let's consider conventional arms, Kalashnikov, for example. The effective distance for the projectile is between 200 meter and 400 meter. And here you can see a distance up to 846 meter. So huge acceleration. So now let me continue with the parallel and perpendicular components of acceleration. Let's consider that we have a constant speed. We have a path like this, a curved path, and then we have a constant speed. So here the direction of the instantaneous velocity like this, and here the direction of the instantaneous velocity always tangent to this curved path. But the acceleration is parallel along the normal here at P point, okay? From the curve to the center, let's say. This is the direction of the acceleration. So how to do that? First of all, you have to calculate delta V, change in the velocity by using vector subtraction, and then you find the direction of the delta V. Then the acceleration is along the delta V. So this constant speed, you can say that the velocity does not change. So why we have acceleration? As I have explained in the previous transparencies, the speed constant, but speed is the magnitude of this vector. This vector has also direction, and since direction changes, we have a delta V, and then we have an acceleration, and the direction of the acceleration is along the delta V. which is parallel to the normal to the path. Do you have any question here? And let me continue with the increasing speed. So here you have velocity 50 km per hour. Here you have instantaneous velocity 80 km per hour. Here you have 100 km per hour instantaneous velocity. And then acceleration is along this direction, not parallel to the normal at p, okay? The direction of the instantaneous acceleration is this one. Why? If you calculate delta v by using the vectors, here you will have bigger vector compared to the previous vectors, then delta v will be in this direction. By using vector subtraction, you can get this direction. If you have a decreasing speed, then this acceleration points behind the normal at p. You see, speed is constant, acceleration is normal to the path, and then if speed is increasing, then this is the acceleration direction, points ahead of the normal, and if the speed is decreasing, then acceleration points behind the normal like this. Do you have any question related to these three transparencies for different speeds of the particle on a curved path? Okay, then let me continue. So let's consider this situation. Here we have an acceleration. Let's consider this is x-axis and this is y-axis. And then you can calculate x component and y component of this acceleration vector, right? So you can do it here. Or you can also choose another coordinate axis like this. As I told you, coordinate axis depends on you. Like here, you can choose that the coordinate axis like this. This is the x-axis. This is the y-axis. Tangent to the path, we have y-axis, and normal to the p point, normal to the path, we have x-axis, and then you have x component of acceleration, and you have y component of acceleration. Any question? These are the components of acceleration. Then let's discuss the two different situations. Here, acceleration parallel to the velocity. So what we have here, this is v1, initial velocity. This is v2, final velocity. And what do you see here? The direction of v1 and the direction of v2 are the same along this direction. But this has bigger magnitude. Then we have delta v here, and acceleration is along the delta v. So acceleration parallel to the velocity. Changes only magnitude of velocity. Speed changes, direction does not, okay? But if you have a curved path, then acceleration perpendicular to the velocity. So what we have here, as we have discussed in the previous transparencies, this is v1, velocity 1. This is velocity 2. Magnitude of v1 is equal to magnitude of v2. Only their directions are changing. So then we have delta v like this, and the acceleration is along the delta v. It means that perpendicular to the path. So this is the difference between circular motion or motion along a curved path and also motion along a straight line. So accelerations have different directions for these two different types of motion. Do you have any question? Here I show you a bio application from the book. So these are the horses, and they are running along a curved path. So what do you see here? That the horses are leaning like this, okay? So by leaning to the side and hitting the ground with their hooves at an angle, these forces give themselves the sideways acceleration necessary to make a sharp change in direction. So what is the direction of the acceleration here? The direction of the acceleration from this to the concave side of the path. Okay, so now let me give you a conceptual example from the book again. Here you see a skier moves along a sky jump ramp. Okay, the ramp is straight from point A to point C. So here point A, point B, and point C. Here we have a straight line. Okay, and starting from C, we have a curved path like this. C, D, E, F, okay, curved path. And the skier speeds up as she moves downhill from point A to point E. She is speeding up until that point, okay? And then she slows down after passing point E. She slows down here after passing point E. So derive the direction of acceleration vector at each of points B, D, E, and F. So here the direction of the acceleration is in this direction. Okay, the lady skier is speeding up, and this is the direction of the acceleration. And whenever she reaches to the curved path and speeding up, so this is the of the acceleration since she is speeding, and here she has acceleration in this direction, and since after passing E point she slows down, then the direction of the acceleration is like this. As we have discussed, three transparencies here: decreasing speed, increasing speed, and constant speed conditions. Here, this is the conceptual example. Do you have any question here? Okay, now let me continue with the projectile motion. So what is projectile motion? Here we have x-axis and here we have y-axis, and this is a vertical plane. A projectile is any body given an initial velocity. Here we have v0, initial velocity, then follows a path determined by the effects of gravity and air resistance. Okay, in many calculations we will omit the air resistance, but in real applications air resistance is very important and you have to take it into account. Now let's consider there is no air resistance and also neglect the curvature and rotation of the Earth. Okay, so this is the Earth's surface, and let's consider it is not a curve. Okay, so what we have here, if you throw a particle with some certain velocity which is given by v0, it has this type of trajectory. So what are the effects? Air resistance is neglected, and we have only gravity acting on this particle. Okay, this is the positive y direction, and gravity acceleration due to the gravity is opposite to the positive y direction. It is along the negative y direction. So for this reason, we choose AY is negative g. Okay, and what about AX? Do we have any acceleration along the x-axis? No, we have just initial velocity and we have no acceleration along the x-axis. But along the y-axis, this particle will always feel a negative g. Okay, so a projectile moves in a vertical plane that contains the initial velocity vector v0. Its trajectory depends only on v0 and the downward acceleration, this one, due to gravity. So now let's try to find the components of this motion, projectile motion. This is the x-axis, this is the y-axis, and this is the V0, initial velocity. This is the alpha 0, initial angle between x direction and also V0. So this is the x component of V0. This is the y component of V0 here. So what do you expect? We have gravity, negative acceleration here along the negative y direction. So this initial velocity along the y-axis will be smaller and smaller. Finally, here at the top of the trajectory, the initial y velocity will be 0. And then initial y velocity will increase again. Okay? What about initial x velocity? Initial x velocity never changes. It is always constant if there is no air resistance. So this is the initial x velocity at position 1, x velocity at position 2, and x velocity in position 3, okay? So here, what do you see? The behavior of y velocity. At the beginning, we have y component of this V0, and it is big. And due to the g, negative g, the velocity decreases, and at the top of the trajectory, it becomes 0, and then it goes back and velocity increases, okay? This is free fall motion, okay? Very nice example of free fall motion, which we have discussed during the last lecture. So in a projectile motion, we also have a free fall motion, okay? The motion along the y-axis or y component of the motion is a free fall motion if air resistance is neglected. Do you have any question here? So if air resistance is negligible, the trajectory of a projectile is a combination of horizontal motion with constant velocity, x component is constant, and vertical motion with constant acceleration. Acceleration is given by the gravity. So you can split projectile motion into these two motions, and then you can easily solve it. Do you have any question related to the components of projectile motion? So now let's discuss the components of acceleration. Along the x-axis, there is no acceleration, it is 0. Along the y-axis, we have negative g if air resistance is 0. But here we have negative g because I have chosen this direction, positive y direction. If I would choose the positive y direction here and negative y direction is this one, then the ay will be positive. Depending on your choice for the positive y direction, you will have negative g or positive g for the acceleration along the y-axis. So what do you see here? We have 0 acceleration. Acceleration does not change. It is always 0 here along the x-axis. And acceleration along the y-axis, it is also constant. Always negative g, right? So we have constant acceleration motion. For the constant acceleration, we have calculated some equations during the last lecture, 4 equations. So I can use these 4 equations for the projectile motion. So remember the first equation. What was first equation? Vx was equal to V0x plus AXT, right? This was the first equation. The second equation was x0 plus V0xt plus 1/2 AXT square, right? And you can also write these two equations for the y-axis, Vy, V0y plus AYT, y0 plus V0y plus 1/2 AYT square. We have done during the last lecture. So what is AX? ax0, so here we have 0, okay? So Vx is equal to V0x. It means that the initial velocity along the x-axis never changes. It is constant. Okay. What about the final position? Final position is given by x0 plus V0x times t. And what about the motion along the y-axis? Vy is equal to V0y. Instead of ayt, here we have negative g times t because we have chosen positive y direction here. This is positive y. Then here we have ay with negative g. Okay, for this reason here we have negative g. Then y, final position. So this is the position 1. This is the maximum height. This is another position here. This is another position along the y, let's say. Okay, so you can calculate the position along the y-axis by using this equation, y0 plus v0y times t. Instead of plus 1/2 ayt square minus 1/2 gt square, because instead of here ay, we use minus g. Any question here related to the equations for projectile motion? You have learned nothing new, okay? You already know of this information from the previous chapter. As I told you during the last lecture, if the acceleration is constant, we have 4 equations for the motion along a straight line, and these equations are very useful also for this chapter and also for the forthcoming chapters. Any question here? Then let me continue. Here we have V0, and this is the x component of V0. This is the y component of V0. And this is the alpha 0, initial angle between x and this V0 vector. So now let's try to write this component in terms of this one and this one. Here we have a soccer ball, okay? And then you hit this soccer ball and you have certain initial velocity which is given by V0, and this is the alpha 0. So the x component of this velocity is given by V0x, V0 times cosine alpha 0. And then y component of this velocity is given by V0y is equal to V0 times sinus alpha 0. You know this information from trigonometry. And then this soccer ball will have a projectile motion like this. Okay, very nice example of a projectile motion. Now, by using these components, look at this one. Here we have V0x, here we have V0x, here we have V0y, V0y. So instead of V0x and V0y, just use this V0x and V0y in these equations. Then finally, you will have these expressions for the projectile motion. And in addition to that, if you consider that the initial x position is 0 when the time is 0, and if you consider that initial y position is 0 when the time is 0, then here in this term, x0 will be 0. Here, y0 will be 0, okay? Then x will be equal to v0x times t, y will be equal to v0y times t minus 1/2 gt square. So instead of v0x, instead of v0y, just write this components contains cosine alpha 0 and sinus alpha 0. Then finally, we have these equations for projectile motion. X is equal to V0 cosine alpha 0 t, and Y is equal to V0 sinus alpha 0 t minus 1/2 gt square, and Vx is given with this one, Vy is given with this one. You don't have to keep these equations in your mind. if you know the 4 equations of motion for a constant acceleration, then you can easily derive these equations by yourself. Do you have any question here? Then let me continue with the position vector. Let's say this is your new position and you would like to get the information about the position vector from origin to this position, okay? And how to calculate this R, position vector. Position vector, or the distance from origin to the projectile, is given by square root of x squared plus y squared. So, and the speed or magnitude of projectile is given by v, which is equal to square root of vx squared plus vy squared. And the angle tangent alpha is given with vy over vx. Look at this one, alpha vy over vx, okay, tangent alpha. Here in this equation, look at this one. Here we have time. If you take time from this equation, you can get x over this term. And instead of t here, just use this t. Let me do it by pen. Here I have equation for the x. And from this equation, I would like to calculate t, time. I can write it like this. V0 cosine alpha 0, right? So just take this t and use it here and use it here. Then I can find relation between x and y. Since this t contains x here, so here we have y, which is given by tangent alpha 0 x minus g over 2v0 square times cosine square alpha 0 times x square. So what do you see here? This y depends on x and depends on x square. Alpha 0 initial angle is constant. G is constant, initial velocity is constant, alpha 0 is constant. So here I have a constant number, let's call it as B, and here I have a constant number, let's call it as C. Then this equation becomes like this, B times X minus C times X squared. So from the mathematics, you can easily understand that this is the equation of a parabola. What is parabola? This is a parabola, okay? This is a parabola, which is given by bx minus cx squared. This is the x, this is the y. Any question here? So projectile motion, perfect projectile motion. If the air resistance is 0, then you will have this type of parabola behavior. Here, there is a ball, and this ball has bounces, okay? What do you see here? Successive peaks decrease in height because the ball loses energy with each bounce, which we don't deal with this explanation now. But what do you see here? The behavior, initial velocity here, and then maximum height, and then y velocity increases again, okay? So this behavior is a parabola. This behavior is a parabola, okay? This is a projectile motion. But for real applications, for real life, you cannot neglect the air resistance. Otherwise, you will have very bad problems. For example, if you consider this howitzer, fırtına howitzer, this is a projectile, okay? If you neglect the air resistance, then you will have very bad situations. And in your calculations, you have to include air resistance, okay? But then the calculations become more complicated. Acceleration will not be constant due to the air resistance, okay? If there is no air resistance, we have just acceleration due to the gravity. But if we have air resistance, acceleration will be different and it will not be constant. And you cannot apply 4 equations of motion for constant acceleration because the acceleration is not constant in case of if we have air resistance. And effects can be very, very large. Maximum height will decrease. Maximum range will also decrease due to the air resistance. And trajectory is no longer a parabola. It will not be a perfect parabola. Here we have 2 conditions, okay? I will compare them. This is the x-axis, this is the y-axis, and we have a baseball, okay? This is the initial position and initial velocity of the baseball. Initial velocity is given by 50 meters per second, and alpha 0 is 53.1 degree, okay, here. And if there is no air resistance, let's consider you throw this baseball with this velocity and angle in vacuum condition, there is no air resistance, then you have perfect parabola behavior of the baseball, okay? But if you consider air resistance, then the maximum height of the baseball is less than this case, and also the range along the x-axis. This is the range if there is no air resistance, and this is the range if there is air resistance. And the behavior is not a perfect parabola now. This is symmetric, very perfect parabola, but it is not a perfect parabola, okay? So this projectile motion in the fırtına howitzer and also for many defense applications and also for the soccer ball and also for the baseball, you have to consider air resistance, okay, in your calculations. But within this chapter and also within the problems at the end of this chapter, usually air resistance is neglected. Do we have any question here? So at the beginning of my talk, I ask you a question, which hits the ground first? You have a red ball, you just leave it, and then it has free fall motion. And there is another ball with yellow color, you throw it in horizontal direction, okay? So which one hits the ground first? They hit the ground at the same time because the time to take the pass from this initial position to the final position along the y-axis is same. So this has free fall and this has a projectile motion. And you know that projectile motion has 2 components. One is horizontal motion with constant velocity, and the other one is vertical motion with constant acceleration, okay? If you choose positive y here with minus g. So balls, this red ball and yellow ball have free fall motion in their movements, okay? So they hit the ground at the same time. So this was the answer of the question at the beginning of my lecture. And then let me finish this lecture with this example. There is a motorcycle stunt rider. A motorcycle stunt rider rides off the edge of a cliff. Just at the edge, his velocity is horizontal. The velocity is along the positive x direction, let's say. Let's say this is the positive y direction. And this bike has only velocity along the positive x direction. The magnitude of the velocity is 9 meters per second. Find the motorcycle's position, distance from the edge of the cliff, and velocity 0.5 seconds after it leaves the edge of the cliff. After 0.5 seconds, what is the position, what is the velocity, and what else? What is the distance from the edge? You can use the equations which we have learned in the previous transparencies. So what do you have here? This is the positive y direction. Then the AY acceleration along the y-axis is given by negative g because this is the ground, and this bike will have this type of motion, free fall, okay, along the y-axis, and it has also motion in horizontal direction along the x-axis, and this is the trajectory of the bike, okay. This is the trajectory. Let's say like this. You can consider that this is the final position, okay? So the motion along the y-axis is a free fall with negative g, and the motion along the x-axis is a motion with constant velocity v0, okay? So by using the equations which you have learned in the previous transparencies, you can calculate the position x here, which is given by v0x times t. Time is 0.5 seconds, and then you can calculate the position. It is 4.5 meters from the cliff, this distance. And then for the y position, you have this term here. If the initial velocity along the y-axis is 0, then this term will be 0. So for the motorcycle, the initial velocity along the y-axis is 0. So v0y is 0. And v0x is different from 0. For this reason, you can calculate y just by using this equation. Put 0.5 seconds here. Then we have minus 1.2 meter. What is this meaning of this negative sign? So since we have chosen this is positive y direction, this is negative y direction, then the position will be negative 1.2 meter, okay? Because the negative side, don't forget. And what about the position vector? It is given by square root of x squared plus y squared. So we have calculated them, put them here, and then you can find 4.7 meter. This is the distance from the origin after 0.5 seconds. And then what about the x velocity? X velocity is constant. So here we have Vx is equal to V0, and Vy at the beginning, Vy was 0, but due to the g, we will have this velocity. It is given by minus gt, and the result is negative. Why the result is negative? Because the Vy here, which is given by negative gt, the particle is accelerating along the negative y direction. For this reason, it has negative sign. And you can calculate the velocity, instantaneous velocity, by using this equation, components of the velocity, Vxi plus Vyj, and just use them. You have calculated here, put them here, and then we have this type of velocity. So we have calculated velocity vector when the time is 0.5 seconds, and let's try to calculate the magnitude of velocity vector, which is given by this expression, and then you can also calculate the alpha here. Alpha is given by arctangent Vy over Vz. You have calculated Vy, you have calculated Vx. So alpha is given by arctangent Vy over Vx. Then put them here. The result is this one, negative 29 degrees. What is the meaning of that? The positive alpha is from positive x to the vector here. If you are drawing the alpha from positive x to this side, it is negative, okay? So everything is meaningful. So you have evaluated your solution. And now let me show you an example from the defense industry. This is the plane Hürkuş-C produced by Tai, okay? And then here you see a weapon. The name is Togan. Okay, so let's consider that this Hürkuş-C plane is moving along the positive x direction with constant speed, with v0, okay? It is moving with v0 along the positive x direction, and then weapon is released with v0, okay? Then it will have projectile motion as we have investigated here. Same behavior. The only difference is that here we considered that the air resistance is 0. We have neglected the air resistance, but here there is an air resistance. So for the fire control system within the plane, you have to calculate the real position of this weapon on the ground by using computer programs, okay? So this is very important, then otherwise you can be faced very bad results. Do you have any question? With this transparency, I finished my lecture, and next week we will continue with motion in a circle, and we will finish this chapter.